Okay, so let us come to the formula what we were talking about in the beginning of these slides. There, that Ito's formula is the one which is analogous to the fundamental theorem of calculus, which would be useful to find out the integration, okay, without going to the first principle. So let us read what is written here. Let f is a function from R to R, so only one dimensional, okay, real to real, but it is twice continuously differentiable, and assume that x is a semi-martingale, okay, which has the decomposition m plus a, okay, and this is a continuous semi-martingale. So then p almost surely for every time t from close 0 to infinity, f of x t can be written as f of x0 plus integration 0 to t f prime xs dms. So this much is like, what is coming like fundamental theorem calculus, that okay, f of x t is there and you are taking derivative and then you are also integrating, okay, 0 to t. However, it does not stop here, plus integration 0 to t f prime, this is the derivative of f prime of x s das plus, okay, a and this together, because x is m plus a. So derivative of f and integration with respect to x is the addition of these two terms, and then we add one more additional term here, that is that half of integration 0 to t double derivative of f with respect to integration with respect to the quadratic variation of m, okay. So this is one additional term which arises in this case, okay. So now we discuss Ito's formula. This version is by Kunita and Watanabe from their work in 1967. So here we consider a function, a real value function f from R to R, one dimensional, and it is square, it is continuously twice differentiable, and x is a semi-martingale, continuous semi-martingale, which has this following decomposition: m plus a. M is a continuous local martingale, and a is a bounded variation process, adaptive bounded variation, and continuous process. And then the function f of x t is equal to f of x0 plus integration 0 to t derivative of f of xs dms integration 0 to t derivative of f xs das plus half of integration 0 to t double derivative of f evaluated at xs and integration with respect to the quadratic variation of m, okay. So here we see that these two integration together stands for derivative of f, integration of that with respect to dxs, okay. However, this term, okay, is additional term which does not arise in the classical calculus. If we wish to ask the question that what happens for the special case where xt is not a semi-martingale but just a bounded variation process, okay, the kind of process what we see in the classical calculus. Because in the classical calculus, when we talk about integration, we mean Riemann Stieltjes integration. There we take integrator to be a function of bounded variation. If that is the case, then since it's continuous bounded variation process, so its quadratic variation would be 0. So this part would be 0, this part does not arise, okay. However, so for our case, quadratic variation would be non-trivial, okay, in principle, so we keep it, okay. So that is the Ito's formula. So we are going to actually prove this Ito's formula. It is we are going to prove reasonably in full details. Consequence of this Ito's formula is that this f of xt is also a continuous semi-martingale, okay. We started x as a semi-martingale, and then we have concluded that, okay, since f has this decomposition, because this is from the theory of integration with respect to continuous local martingale, this is also a continuous local martingale, and this part would be another continuous process because the integration would be bounded variation process. And here this would be also, like, these are like still this integrations, these two terms, 0 to t, these are continuous path process. Okay, so this is a local martingale, and this part is the bounded variation process, continuous bounded variation process. So this is also semi martingale decomposition of f of xt. So f of xt is also continuous semi martingale. The initial question that why this formula gives the capability of finding integration thing is that if one is given this type of integration and asked to compute, then one has to find out this function, one to identify this as a derivative of some function, or in other words one should look at the antiderivative of f prime, okay, that is f, and then this integration value can be obtained by calculating other integrations. Okay, so one can obtain these integrations using the classical sense, and these are this f of this value. So therefore this integration value can be obtained by evaluating all other values. Okay, so that is also going to serve the purpose of calculating the integration. So the proof has many steps. So in the step 1, what we do, we actually take a sequence of stopping times. That is important for our case because we would consider the stopping time so that we can localize the integrands and integrators both, so that they are for them we can actually make those as square integrable martingales. Okay, so let us construct this Tn. What is this Tn? Tn is the first time when this maximum of these three things hits n, the threshold n. Okay, for whatever large n, we choose that first time that mod of mt. Mod of mt is the absolute value of the integrator and the total variation of a. Okay, if we have some a non-trivial a here, and the quadratic variation of m. Okay, so either of these, okay, if one of these maximum touches n, then we call that time t for the first time when it touches as Tn, and if never touches, so for example n is large and for infinite time t you wait and the maximum never touches n, then this is an empty set. So empty set by convention is infinity. We are going to take Tn is equal to infinity for those occasions. And why this 0 is that? This is the case where it's a mod x0 itself is larger than n. Okay, then we do not ask this question, we just put this 0. Okay, so when mod x0 is equal to more than n, then we put 0 and we wait for n to cross this mod x0. When x is more than mod x0, then we ask this question, then we define Tn in this fashion. Before that we put Tn is equal to 0 0 0 0 etc. So this is a graphical way of stating what is articulated here, this example of so here consider the semi martingale to be just the Brownian motion w, and then so w, Brownian motion is a not only local martingale, is actually it's a quadratic, is square integrable continuous martingale. And consider the quadratic variation of w, we would later see that, okay, that is nothing but the identity function t itself. So we draw both. So we draw mod of w. See here, say mod of mt. Okay, so for me this mt is x is Brownian motion, a is 0 here for that example, and m is Brownian motion. So this part I need to consider, this part I do not need to consider because a is trivial is 0, and we need to consider these two things. Okay, so mod mt is drawn here. This is a simulation of Brownian motion of one path. Okay, so when it is becoming negative, but mod is pushing it, making it always positive. Okay, the Brownian motion path, and then this is the quadratic variation of Brownian motion, and there n is equal to 1, 2, 3, etc., and x0 is equal to 0. Okay. So T0 is 0 here, but T1 is the first time blue or red, okay, which touches 1. So here red touches 1, so this is T1. Second time when either blue or red which touches the threshold 2, that is my T2. Then T3 is the first time blue or red, whichever it touches 3. So here blue touched 3 first, red touched little later, so T3 is here. Actually around the time T4, actually, you know, the red line touched 3, but okay, but blue line, the mod of the modulus of the integrator is way above there, so this it touched 4th, so now it is, therefore this time is T4. Similarly, therefore this time is T5, this time is T6. So we see that okay, we are getting an increasing sequence of stopping times, T1, T2, T3, T4, T5, T6, it would increase. And then after obtaining this sequence of stopping times, we construct a stochastic stop stochastic process, the localized, that x t minimum Tn. So what does it mean? That okay, so after Tn, say for example n is equal to 4, so if stochastic process is here, and then we are going to put this is equal to same thing, that is constant flat, that would be the sample path for that particular omega. So that is my localization of the integrator. So integrator is localized this way. So here you remember that in this localization I have not used integrands. I mean, I'm not looking at it because you know that here just the, I mean, here integrand is a very special thing. It is actually function of the integrator itself. Okay? We do not need actually general here. The general integrand does not appear. Correct? The integrator is a very special type. Right? It is just a function of the integrator itself. So now we would consider that this xn, okay, so it is sufficient to establish the results for xn instead of x as Tn tends to infinity, as n tends to infinity. Okay, so whatever we would like to establish this, you know, this equation, we are going to establish only for this stopped process xn. Okay, why is it so? Because even if you do for xn, and then t will be replaced by t minimum Tn everywhere, correct, or everywhere T minimum Tn, and then as n tends to infinity, Tn goes to infinity, okay, with probability 1. So right hand side would converge to this almost surely, so left hand side would also go to there. Okay, so we are going to consider only this, you know, stopped process xn. Now for the convenience of writing, we replace x by xn. Okay, next onward. So whenever we say in the next process x, actually I mean x superscript n. Whenever I say m, I mean that m superscript n, etc. I mean that is the that martingale part of xn. Because xn is a semi-martingale, correct, but martingale part of this. Okay, x is replaced by xn for some fixed n, then we get mt. Okay, and total variation of a. Okay, and this quadriviation of m are all bounded by a common constant a, k, because the way we have done. Okay, these are all bounded. And then since I have removed the notation of n, that means there is a fixed n. Okay, so everything is for a fixed n. I'm not letting n tends to infinity anywhere here. Okay, so for a fixed n, so there is a fixed constant k. So the values of f, the function f, outside the interval, so values of function f outside the interval minus 3k and 3k are irrelevant. Why is it so? Because that process does not leave this thing, I mean this interval minus 3k to 3k. Why this 3k is coming? Because, you know, I mean these three terms, I mean the terms are coming. So mod mt is also between minus k to k, this is also minus k to k, etc. So f prime of this, you know, this inside x, okay, does not leave that interval. So for this integration, does not matter what the value of f and f prime, okay, are there beyond that interval. Whatever, I mean, even if it has, I mean, if I take two different functions f1 and f2, which matches exactly the same in minus 3k to 3k, both would have exactly the same, you know, like left hand side, right hand. they would not, because the process does not go beyond this interval. So we can therefore choose f to be a twice differentiable and with compact support. Actually, I can minus 3k, beyond minus 3k to 3k, I can extend the function such that it has a compact support and it remains twice continuously differentiable. So what is the bottom line? The bottom line is that we know that twice differentiable functions with compact support, they're all the first second derivatives are bounded. Okay, so they would be bounded. So now we are in a very good place because the integrand is now bounded, therefore. Okay, it's bounded. So using Taylor's expansion, we can write down f of xt minus f of x0 is equal to, this is obtained by choosing a particular partition pi. That pi is partition of t1, t2, tk, etc., tm. Okay, so this thing is now a telescopic sum f of xt minus f of x0. So that is f of xtk minus f of xtk minus 1. Okay, so here I have not used Taylor's expansion, I have used it here actually. Okay, so this is just a telescopic sum. So all these next, the first term is xt1 minus xt0. So xt0 is, t0 is taken as 0, etc. So that sum, okay, for each and every increment, so it has now m number of increments. For each and every increment, we are going to get, okay, we are going to use Taylor's formula there. Okay, so for that difference, we are going to get expansion. Okay, so that expansion is also written in terms of j1, j2, and half j3. This is second derivative. This involves second derivative. Okay, these two involves first derivative. So where, let me write down what is j1. j1 is the f prime x tk minus 1 times atk minus atk minus 1, and here second j2 is the same derivative, okay, same integrand, but mtk minus mtk minus 1, and j3 is the second derivative, correct, half of that. Okay, that appears, that f double prime, but then derivative is evaluated at some point. Okay, at some point which is between xtk minus 1 and xtk. So how do you write? The eta k is a number which is like xtk minus 1 plus theta k times xtk minus 1, where theta k is between 0 and 1. Okay, so this is a consequence of Taylor's expansion. Okay, so if we expand Taylor's, do expression of each and every term, then we are going to get. However, we have sum over k is equal to 1 to m, so we are getting this sum also, k is equal to 1 to m. This sum is also there. Now let us look at each and every term separately. Okay, so it is a little long proof. Okay, so j1 pi is, this is like f prime xtk minus 1 times atk minus atk minus 1. So atk can be viewed as integrator here, which is a boundary variation process, and here this integrand is evaluated at tk minus 1. Okay, so since it is continuous function of time. Why is it continuous function? Because x is a continuous function of time, f prime is also continuous. So composition of continuous functions. Continuous function of time, it does not matter what we choose. Okay, so and then we are choosing the left point, and then as the mesh size goes to 0, and then this would give me just the Riemann-Stieltjes integration of f prime of x with respect to integrator a. Okay, so this j1 pi would converge to this Riemann-Stieltjes integration as mesh size goes to 0. And that would happen with probability 1. Almost surely we are going to see this. Okay, since f prime is bounded, the bounded total variation of a on 0 t is also bounded. So therefore, this is the bounded random variable. Okay, this bounded random variable, and that measure is probability measure is also 1. Okay, so finite measure, unfinite measure, the bounded sequence of boundary random variable that converges, almost surely that converges in L1 also, correct. We can use actually dominated convergence theorem. Okay, bounded convergence theorem, actually bounded convergence theorem. j1 pi converges to 0 to t f prime xs ds in L1 as mesh this partition mesh size goes to 0. Remember that here we are not taking limit as n tends to infinity, correct, because n I have fixed earlier. and that I am not changing. I am just changing the measure, the partition here, time partitions. Okay. Next is y. What is y? Y is that integrand f prime xs. Why are you looking at this? Because in J2 pi we have this, integrand f prime x tk minus 1, and here the candidate of integrator is the Martingale. Okay, so we need to justify that convergence of the integration. So for that, what do we need to do? We need to actually justify the where is it, okay, which process. So y is in Elster. Why is it so? Because it is continuous, and then it is also adapted, so it is progressively measurable. So it is in Elster. It is actually bound. This is bounded. So all these box norm, finite expectation box. Okay, so that is also true because it's bounded. Okay, so all these conditions we can satisfy. So y is in also Elster. Now for this y, let us look at this. This is like a discretization of this y. Okay, so let us write down this discretization precisely. So this is y pi s for this particular partition, f prime x tk minus 1 indicator function of tk minus 1 to tk, closed tk. So this approximation of this y, if you integrate with respect to Martingale, you are going to get exactly this thing, correct? Exactly this thing. Okay, so this integration. So we are, so to understand J2 pi, we can write down J2 pi as therefore integration of this with respect to the mtk. Okay, so here m due to the localization is a Martingale, correct? It is not in no more local Martingale, it is a Martingale, square integral Martingale. So we are properly in the setting that this is now a sequence of simple processes which is converging to y. Okay, so we can also cross verify this thing. Is easy to cross verify, it is not difficult actually, that using the dominant convergence theorem, that this y pi and y, this box, their metric, box metric, that goes to 0, okay, for each and every time t. And then we know that how to compute the box matrix overall, that for every n, and then you take a minimum of 1 and divide it to the n and sum over all possible n. So that will also go to 0 therefore, okay, for every point it is going to 0. So J2 pi, because J2 pi is nothing but integration of this thing with respect to Martingale, and then this integrand is converging to y in box norm. So we know that, okay, this integration of this y with respect to the square integral Martingale m is just nothing but the limit, okay, L2 limit of J2 pi. So J2 pi converges to this L2 p. Okay, so we have this, so we save this result. Okay, so J2p. Now we should start talking about J3 pi. Okay.